much fun. You're so excited. So I'm going to minimize this so I can always have it visible on the board, at least for the most part, so we can refer back to it. I highly suggest you, as I said yesterday, circle all of these, square all of these, star them, whatever you have to do to remember that we are using these primarily when we talk about trig equations. So the first thing I would like to do is I would like to express sine of theta in terms of cosine of theta, and we're going to be using the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. So what this means is I want to have sine on the left-hand side and some cosines on the right-hand side. I don't want to have anything else in there. I want no other trig functions, nothing. Okay, so as I'm looking at this, to get sine by itself on the left-hand side, what am I going to have to do? Subtract the cosine squared over to the right-hand side. So when I do, I'm left with sine squared theta equals 1 minus cosine squared theta. My goal here was to express sine in terms of cosine, which means I want a singular sine on that left-hand side. So what am I going to have to do next? Square root both sides. So when I do, I'm left with sine of theta is equal to the positive and negative square root of 1 minus cosine squared theta. Right? We are only using the positive, correct? So sine of theta is equal to the positive square root of 1 minus cosine squared theta. We have now expressed sine in terms of cosine. There were no other trig functions present, so I didn't have to do any other identity simplification. So this example was all about just manipulating a Pythagorean identity into what we needed to use it for. Are we all okay with everything we did here?
In terms of cosine, you can't use another equation that has cosine in it. You have to use the one that only has it.
This means I can't have another trig function in there, so I couldn't have a tangent in there or a secant. I would have to somehow rewrite those in terms of cosine as well. So in terms of cosine means I can have no other trig function except cosine in there.
Wait, how do we rewrite?
Well, we're gonna get there. We're slowly easing you in. Slowly is the key word here. And I'm gonna try not to overwhelm you. So we're gonna do a brief kind of equation manipulation today. And then we're going to move on and we'll come back to this because I'm trying not to overwhelm you. This is probably the hardest part of trig, in my opinion. Okay. So let's go ahead and do another example. I'm going to erase this one so that I have the room and we can still see all of our nice, pretty, fun trig identities up there. So on this next example, that off to the side. I would like to show that the following equation pause. I skipped one. Sorry. Hope you're not writing in pen. Express tangent in terms of sine. So this means I want tangent equals, and then I want nothing but sines and whole numbers on the right-hand side. So I need to start with what tan is actually equal to. Any ideas? Well, I know it's 1 over cotangent, but that doesn't really help me because that's not sine. So do I have any identity that has tangent and sine in it? Tangent equals sine over cosine. So that's off to a terrific start because now I have a sine in there somewhere. Okay, so that was our tangent identity. Everyone okay with where that is and where that came from? Okay, I'm not finished because I have a sine and I have a cosine. So now I have to find some way to rewrite cosine with only a sine in it. Do I have any equation or identity that has a cosine and a sine in it other than the tangent one? Say it louder and with confidence.
Sine squared plus cosine squared equals 1.
I have my Pythagorean identity that says that cosine squared plus sine squared equals 1. So I can take that equation and I can manipulate it so that cosine is equal to something that has a sine in it. So I'm going to do that. I'm going to take that equation, or that identity, sorry, and I'm going to manipulate it so cosine equals something with sine in it. So what's the first thing I'm going to do to get cosine by itself on the left-hand side? Subtract the sine squared over, just like we did in this first problem. So now I have that is equal to 1 minus sine squared theta. I have a cosine, so just a singular one in this tangent equation. So I need a singular cosine in this Pythagorean identity. So what am I going to do? Square root both sides. I know I'm taking only the positive version. So I get cosine is equal to the square root of 1 minus sine squared theta. I have a singular cosine here, and I have a singular cosine here, so I can now substitute. I'm going to take this square root, and I'm going to replace the cosine with it. So when I do that, I'm going to have tangent of theta is equal to sine of theta over the square root of 1 minus sine squared theta. So now I have tangent in terms of sine. How do we feel about that?
Great.
That's it for that one. So this whole portion is just about manipulating the identities to simplify this to the requirements. That's all it is. This is the free thinking part of trig that everybody doesn't really care for. And for that, I'm sorry. Does everybody understand everything that we did here and why we did it? Anybody confused? If you are, please speak up. Please, please, please. Okay, so let's go ahead and do another example. Again, I'm going to erase this so we can keep our Pythagorean identities right here as an easy reference.
That was still.
Right? We only have, I believe, 2 more examples of this, and then I'm going to give your brain a break.
Like this one and one more, or like this one and 2 more?
No, this one and 1 more. Bless you.
Bless you.
So now we're introducing the concept of an identity. So an identity is an equation that works for every single angle theta. Okay, so the one way that we can test for an identity is we can plug in angles and try to find one that doesn't work. If we can't find one that doesn't work, we assume it's an identity. Another way of proving an identity is I take my equation and I simplify one of the sides until it matches the other side perfectly. Okay, that is sometimes the easiest route because sometimes it's really hard to find one that doesn't work even though one exists. Okay, so in this particular example, I'm going to be taking something I already know is an identity, and I'm going to prove that it's an identity by simplifying one of the sides down until it matches the other side of the equal sign. So the identity I'm going to be working with is secant theta plus tangent theta times 1 minus sine of theta equals cosine of theta. So what I'm going to do is I'm going to work with this left-hand side only, and I'm going to keep simplifying it using all of my identities until it matches that right-hand side. I know that seems impossible, like how in the world is this product going to match that, but it will. If you need to remember that we're only working with one side, some people choose to draw a vertical line through the equal sign, indicating I'm separately working with one side of this equation. Whatever works for you is what I want you to do. So as I'm looking at this right now, is there anything that I can do right away that's like really, really apparent to me? I couldn't think of anything either. So when we're at a loss, we look at two things. We look at our reciprocal and tangent and cotangent identities, and we look at our Pythagorean identities, because something there is going to give me a clue about what my first step should be. I don't have any squares in this, so it's not going to be one of my Pythagorean identities, which means I'm either looking at the reciprocal identities or the tangent and cotangent identities, or maybe both. What do you guys think? Are we going to be looking at the tangent ones or the reciprocal, or both? Both. I know I can work with the tangent identities because I have a tangent in here, and I know I can work with the reciprocal identities because I have a secant, and I know its reciprocal is cosine. So I'm going to work with those identities, and I'm going to rewrite what I have into whatever they're equal to. So secant is equal to 1 over cosine, so that's what I'm going to rewrite it as. Tangent is equal to sine over cosine, so that's what I'm going to rewrite it as. So rewriting this using those, I'm going to have 1 over cosine of theta plus sine of theta over cosine of theta, still in its parentheses, times 1 minus sine of theta. Everyone okay with what I did there? Sometimes it's helpful to write what we used off to the side until you get used to this. So off to the side, you could write that secant theta equals 1 over cosine of theta, so you remember that you used that reciprocal identity. And we can write that tangent of theta is equal to sine over cosine to remind us that we used that tangent identity. Whatever works for you is what I want you to do. So if you need these reminders, write them down. So now I'm looking at what I have here. I have 1 over cosine plus sine over cosine, all times 1 minus sine of theta. Looking at this now, is there any way that I can simplify this or rewrite it so it's easier to look at before I continue to simplify? Yes, how, Becca? These two fractions have the same denominator, which means I can write them as one fraction, each or with the common denominator of cosine. So this becomes 1 plus sine of theta over cosine times 1 minus sine of theta. So I just simplified that first parentheses into one fraction. As I'm looking at this, there's really none of the identities that I can use because I already used the reciprocals. I already used the tangents, and nothing would really help me simplify this anymore. So now I'm looking at these two parentheses, and I have to ask myself, what's the next logical step here? Anybody have an idea?
Could you like multiply both sides by like, or like make it a fraction over itself and then multiply to cancel out?
We could, but that's actually kind of just going to bring us back to where we were before. But what I could do instead is I could FOIL this out. So I'm going to take 1 plus sine of theta times 1 minus sine of theta, and my answer is going to be over cosine, and then I'm going to see if I can simplify further from there. Okay, sometimes we have to make it uglier before it looks nicer. So let's go ahead and multiply that out. It will be a FOIL because it's a binomial times a binomial. So when I do that, 1 times 1 is 1. 1 times negative sine is negative sine. Sine times 1 is positive sine. And then sine times negative sine is negative sine squared. And then that's all over cosine. So I just went ahead and simplified that out, or FOILed it out. What can I do from here? Combine like terms. So my sines cancel, and I'm left with 1 minus sine squared theta over cosine of theta. Now I'm kind of stuck again. Ooh, say it again, Marissa.
Is that the
Pythagorean identity, right? Because I have a Pythagorean identity that has a 1 and a sign in it. It doesn't look like this, but I can make it look like that if I need to. I know that I can use a Pythagorean, or I'm pretty sure I can use a Pythagorean identity here because I have a square. So anytime an exponent becomes introduced, we should check our Pythagorean identities on the next step. So if I go and look at those, the Pythagorean identity I have that has a sign and a 1 in it is this one. Can I manipulate that Pythagorean identity to become 1 minus sine squared on one of the sides of the equal sign? Yeah, all I have to do is subtract the sine squared over. I like to write it out to avoid any issues. So what I have is sine squared theta plus cosine squared theta equals 1. I need it to become 1 minus sine squared theta on one side of the equal sign. So I'm going to subtract it over. And I get cosine squared theta equals 1 minus sine squared theta. So what I'm going to do now is I'm going to take the 1 minus sine squared theta that I ended up with here, and I'm going to replace it with what it's equal to there. So I'm going to replace that 1 minus sine squared theta with cosine squared theta because that's what it's equal to. When I do, I'm left with cosine squared theta over cosine of theta. I know I'm on the right track because I'm trying to get it to match cosine of theta on the right-hand side. So I'm definitely doing okay so far, but I'm not done because I have a fraction. Okay, so we can remember that cosine squared theta is the same as cosine of theta all squared, or cosine times cosine. So if I think about it like that, one of my cosines from the numerator will cancel out my cosine from the denominator, leaving me just with cosine of theta. Am I finished? Yes, because my left side matches my right side. So I always like to end this by showing that I have made them equal and then putting a check mark. I have now proven this identity by simplifying the left-hand side until it was equal to the right-hand side. How did we feel about that one?
That was absolutely.
As I said, this is typically the least favorite part of the whole trig semester.
Why would you do it right at the very beginning?
Did anybody like it? Some people do. No? Very a little sad right now. And this is kind of like simplifying equations was first semester. You have to kind of guess to know where to start. I will also tell you there's more than one way to simplify this. Other ways just will take more steps, and that's perfectly fine. If you didn't automatically think about it this way, there were other ways you could have started this. Okay? And other like avenues pretty much you could have taken to simplify it. Let's go ahead and do another problem. This will be the last trig equation one that we do, because I know your brains are getting thoroughly fried. Gosh. Okay, so our identity here is tangent theta plus cosine theta all over sine of theta is equal to secant theta plus cotangent theta. We're going to be doing the same thing here. It told me that I'm going to be simplifying the left-hand side until it matches the right-hand side. So I'm going to go ahead and draw my vertical line so I remember I'm treating these as independent expressions. I'm also going to let you know that it's not always going to tell you which side to simplify. And sometimes you'll have to simplify both sides until they will match. Okay, so we are going to slowly make this a little bit harder. Not much harder because it is already kind of a difficult concept, but it won't always expressly tell you where to start. Okay, so now that we have this written, does anybody have an idea of where we're going to start? Ismail.
So since you have cosine over sine, you can have a cotangent. Cotangent out of that if you take out the tangent on top.
Okay, but I can't just get rid of that tangent on top.
Well, aren't they two separate things?
Say it again, or tell me what you're thinking more explicitly.
It's tangent over sine plus cosine over sine.
I can separate this one fraction into two separate fractions. So the opposite of what we did on the previous problem. This would allow me to identify those other identities that are happening. So the first thing I'm going to do is I'm going to separate this into tangent of theta over sine of theta plus cosine of theta over sine of theta. Everybody see what we did there?
Should we just put secant for cosine over sine? You already have it.
Not secant.
Oh wait, sorry, cotangent.
Okay, so the first thing Ismail notice is that cosine over sine is equal to cotangent. That's awesome. We can go ahead and put that in there. So what I have now is I have tangent theta over sine of theta plus cotangent of theta. This is good because I've already matched half of my identity. So the only part I have to work on now is transforming this fraction into secant of theta. So we're kind of already halfway there. Anybody have an idea of what I can do to somehow transform tangent of theta over sine of theta into secant of theta? Or a step along the way? Ismail, you cannot answer. I want somebody else to think about it. Gabe cannot answer either. I know, sorry, you can't do it.
I got excited actually. Good. I'm not saying.
I have a tangent and I have a sine. So that means I can do one of two things. Marissa, what are you thinking?
That one and that one.
The tangent identities? Okay, so I have a tangent identity. This is tangent is equal to what? Sine over cosine. So I can actually replace that tangent with sine over cosine. However, it's going to get a little messy because I'm going to have a fraction within a fraction. So my suggestion first is to separate this into tangent times the fraction 1 over sine of theta, which might make it a little bit easier to manipulate. So this is going to become tangent of theta times 1 over sine of theta, and plus the cotangent of theta we already did. This allows me to go ahead and transform tangent of theta into sine over cosine, which means I have sine of theta over cosine of theta times 1 over sine of theta plus the cotangent of theta.
The 1 over sine, isn't that like the reciprocal thing?
We could use a reciprocal here. However, I think I want to simplify first because that might lead to some unnecessary steps. Say it, Nicole. The signs cancel. Because I have a sign on top and I have a sign on the bottom, which means what I have left is 1 over cosine of theta. So I have 1 over cosine of theta plus cotangent of theta.
You know what that equals?
Oh my gosh, Colin's going to tell me.
It's a reciprocal.
It's a reciprocal identity. 1 over cosine is equal to what? Secant. So now I have secant of theta plus cotangent of theta equals secant theta plus cotangent theta, which is exactly what I wanted. See, it's kind of fun. When it all comes together, it's beautiful.
I like it, but I mean, I know these just seem simple. These seem simple enough, but once we add other numbers to like angles.
Well, yeah, I mean, like, it's always gonna get a little bit worse, but.
A little bit, no, it's gonna be way more scary.
Okay, how did we feel about this particular example? Okay, the more we do these, the easier they are going to become. They're never gonna be super duper easy. Even I sometimes stumble over them occasionally. It happens.
That makes me feel good.
It should. As I said, there are numerous ways you could have done this. There's not just one particular way that is the absolute right way of doing it. So when you find one that works for you, or you maybe identify something that we didn't identify, that's okay. It might lead you in a circle and you have to start over again, but it's all a learning process, so that's okay. I love it when I see somebody do that, actually. Okay, any questions on this one or the other ones we've done? Because this is the last one I was going to throw at you today, because I know it's rough. So what we're going to look at now is we're going to look at angles on a unit circle, or on a circle in general, actually. Let's see what time it is. 20 minutes? I could do that. We could do that.
4 day less.
Or would you rather I didn't and I saved it?
What's the alternative of doing this more?
Homework time.
Okay.
I say save it.
Okay, so I feel that I have adequately fried your brains, which means now it's going to be homework time. Tomorrow we will finish up the lesson. What we have left is actually not posted in your notes. I will post the updated version of the notes because I added to them. But it is angles on a given circle, which leads us into our unit circle, which is what we're going to start building next week. Okay?
All of them?
No. We're building our unit circle next week. So Mackenzie right now is homework